All right, in the last part, we saw what kind of stress distribution and what kind of deformation we should expect for every type of load that we can apply on a certain beam. Now we are going to look at most common cross sections that we can find for every specific load. So we start, and we will look also at what kind of information we need in order to apply the equations that we saw last time. So we can start with the axial load. We know that the equation that we use is sigma equal to P over A, so normal stress equal to axial load divided by cross section. So basically this equation can be applied to any type of cross section. The shape of the cross section doesn't really matter in this case. The only thing that we need to know is the area of the cross section. So we can have a square cross section, rectangular cross section, or circular cross section, can be hollow, can be solid, can be an I-beam, can be a channel, any type of shape. We will always use this equation because we only need to determine the area of that cross section. All right, then we can move to the torsional load. We saw that the equation that we use to determine the stress is tau equal to T over J. So in this case, actually, this specific equation is used for circular sections only. We can use the equation for also other type of sections, but that requires a little bit more attention. So right now, let's focus on circular cross sections. So in this case, the parameter that we have to use is the polar moment of inertia, and the polar moment of inertia of a certain circular cross section. So if this is the cross section and we have the radius r, the polar moment of inertia, or again of a circular cross section, is equal to pi r to the power of 4 divided by 2. So this is what we have to use when we want to determine the stress and also actually the angle of twist when we apply a certain torsional load on a circular cross section. Of course, this is valid also for a hollow cross section. So if we have a circular hole in the cross section, we just need to calculate the polar moment of inertia of the hollow cross section as the difference between the polar moment of inertia of the external circle and the polar moment of inertia of the internal circle. So let's now move to the bending moment. And for the bending moment, we can have different types of cross sections that we can use to build beams that need to support this type of load. So we can start from the most simple cross section, which is like a rectangular cross section. So just a reminder, the stress that we obtain is a normal stress, and the equation is m over I times c. So basically, in terms of information from the cross section, basically we need to look at the moment of inertia of the entire cross section. So depending on when the bending moment is applied with respect to an horizontal axis or with respect to the vertical axis, in this case, we need to find the specific moment of inertia. So if we have that x is the horizontal axis and y is the vertical axis, also if we indicate with b the width of the beam and with h the height of the beam, we can have that the moment of inertia with respect to the horizontal axis is given by b h cube over 12. On the other hand, if we want to calculate the moment of inertia with respect to the vertical axis, Iy, that will be h b cube over 12. So we just basically flipped the two dimensions of the cross section. So another case that we can find when we have beams subjected to a certain bending moment is the case of an I beam. So in this case, what we need to do, we need to look at the different, let's say, subsections of the cross section. So the easy way, let's assume that we have the same y and x axis. Also, we assume that this distance is b. Then we have the height from here to here, which is h. And then we also have that the thickness of the top flange, bottom flange, and web are all of them here. So in this case, what we have to do, we have to divide basically the cross section in 3 portions. So we have the top flange that we can indicate with 1. Then we have the web that we indicate with 2. And then we have the bottom flange that we indicate with 3. So the moment of inertia with respect to the x-axis will be given by the summation of the moment of inertia of top flange, moment of inertia of web, and moment of inertia of the bottom flange. So we have I1 plus I2 plus I3. Now we can analyze the moment of inertia of each portion of this beam. So let's start with I1. So I1 would be the moment of inertia of this portion here with respect to the x-axis, to the horizontal axis. And in this case, what we have to do, we have to apply the theorem of the parallel axis. So in this case, the moment of inertia of this top flange with respect to the horizontal axis is given by 2 terms. So we have the first term will be the moment of inertia with respect to its own axis of symmetry, which would be b t cube over 12. And then we have to add another contribution, which is basically telling us that the area that we are considering is not aligned with the axis that we are looking at, but it has some distance. So in this case, we have to, this term is given by the product between the area and the distance squared. So the area would be b times t. And then the distance is the distance between the horizontal axis and the center of this area here. So basically we have, in this case, h over 2, which is half of the cross section, minus t over 2, because it is half of the top flange. And in this way, we took care of the top flange. Then we can look at the web, the web I2. In this case, the axis of symmetry of the web, so section number 2, is aligned with the axis that we are considering. So we don't need to apply the theorem of parallel axis. So we just need to consider the moment of inertia of this web with respect to x, and we use the same general equation that we used before. In this case, our width would be the thickness, because we said that all three have the same thickness. The height would be this quantity here from the bottom of the top flange to the top of the bottom flange. So which means we have h, and then we have to remove 2 times the thickness. And of course, we have to divide by 12. Then we have the third portion, I3. So the third portion is symmetric with respect to the first portion. So the top flange and the bottom flange are the same. So which means that the contribution of the of the bottom flange will be the same of the contribution of the top flange. So basically, we have that I3 is equal to I1. And then once we have all the dimensions of the cross section, so the height, the base, and the thickness, we can apply these equations so that we can obtain the moment of inertia with respect to the horizontal line. Another cross section that we can find sometime subjected to a certain bending moment is a circular cross section. I use a little space here. So in this case, the moment of inertia with respect to the x-axis would be the same of the moment of inertia with respect to the y-axis. So we have that Ix is equal to pi r to the power of 4 divided by 4. All right, the last load that we can analyze, as we did before, is the shear force. All right, as we said before, in order to determine the shear stress, we can use the shear formula, which is VQ over IT. So now, actually, we can use even more simplified versions of this equation. So we can estimate the shear stress on a certain beam by using the average, the equation that gives us the average shear stress. So this is something that can be used when we have a pin, for example, or when we have cross sections that are not too thick in comparison with the rest of the dimension of the beam. Again, this is a approximated equation, but gives a rough estimation of how the stress, the shear stress would look like. So in this case, we have that the average shear stress is simply given by V divided by A. So where V is the shear force and A is the cross section. So this equation here would be actually analogous to this equation here. But again, remember that this gives only an average of the shear force on a certain cross section. If we want to look at how to apply the shear formula for certain cross section, one cross section we can analyze is certainly a circular cross section. And when we have a circular cross section, we know that the maximum shear stress that we obtain is at the neutral axis. So in the case of circular cross section, the neutral axis is in the center of the circular cross section, and in order to obtain the shear stress, the exact value of the shear stress at the neutral axis, we can use the equation VQ over IT. So we can explore now the meaning of all these terms for again the circular cross section. So we have that B is of course the intensity of the shear force applied at that specific location. Then we have Q, that is the static moment of the portion of the cross section above the location at which we want to determine the shear stress. So in this specific case, since we want to determine the shear stress this location here, because we know that here we have the maximum shear stress, we have to calculate the static moment of this portion here. So the top half of the circle. So the static moment again is a product between a certain area and a certain distance. So in particular, the area would be the area of the portion that we are considering. So in this case would be half of the circle. And then the distance is the distance between the center of gravity of that cross section, excuse me, of that portion of the cross section, and the location where we want to determine the shear stress. In this case, would be the diameter. So the distance that we are looking at would be approximately this distance here. So for a circular cross section, you can find this in tables, and we have that this distance is 4/3 r over pi. So this will be how we write the static moment. We want to determine the shear stress at this diameter for a circular cross section. Then the other component that we have to look at is the moment of inertia. In this case, the moment of inertia is the moment of inertia of the entire cross section. So in this case, the moment of inertia of the entire circle with respect to this horizontal axis. And it is given by 1/4 pi r to the power of 4. And then the last component that we have to look at is the thickness at the location at which we want to determine the shear stress. So in this case, we want to determine the shear stress here. So this means that we have to use the diameter as thickness. So it would be T equal 2 times the radius. Then when we combine all these equations with this equation here, what we obtain is that tau max is equal to 4/3 so we have 4/3 v over pi r squared, which is also equal to 4/3 v over a. So as you can see, when we use the exact solution for the exact equation for the shear stress, so if we use the shear formula instead of using the average shear, we obtain a value of the stress, of the maximum stress, that is actually higher than the average stress that we would obtain by using this equation here. So it means that if we want to look at the failure of that specific cross section, we cannot base our judgment on the average stress, but we need to look at the actual maximum stress that occurs on the diameter, which will be the neutral axis of the cross section. So we can look at at another cross section that we can typically find when we have a certain shear force. So I'm going to copy this equation here so we have more space. And now we can look again at a rectangular cross section. Even in this case, we have B and H. And even in this case, we could use the equation tau average equal to V over A. But if we use the shear formula, we will obtain a more correct result. We also know that the stress distribution is a quadratic distribution. We know that the maximum shear stress occurs at the neutral axis. So we are going to focus on determining the shear stress at the neutral axis, which in this case is in the middle of the height, of h/2. So we can go through the same process that we followed before. So we have that tau max equal to VQ over IT, and then we can look at each term that we have here. So let's start with Q, as we did before. Again, Q is the static moment of the portion of the cross section above the location where we have to find the shear stress. So in this case, we are looking at the static moment of this portion here. Above the top half of the cross section. So as we did before, the static moment is the product between two quantities. The first quantity is the area of this portion, which in this case would be B times h/2. And then the second term here is the distance between this line here, the neutral axis, and the center of this portion. So here our distance will be this, which in this case is h/4. And this is the static moment. We can look at the moment of inertia. So the moment of inertia would be the moment of inertia with respect to a horizontal axis, in this case, when we have the shear force applied in this direction. So the moment of inertia, we saw this equation here, so bh cubed over 12. And then the last term that you have to look at is T, which is again the width of the beam, the width of the cross section, where we want to determine the shear stress. So in this case, it will be equal to V. So even in this case, we can combine all these equations together, and what we obtain is tau max (3/2 V/A). So as you can see, even in this case, if we use the average equation, the equation to determine the average shear stress, we would obtain V/A. But if we go through the shear formula, what we obtain is 3/2 V/A, which is 1.5 V/A. So it means that the maximum shear stress on a rectangular cross section is actually 1.5 times bigger than the average stress on the entire cross section. So again, if we want to estimate the shear stress, we can use the average equation. But if we want to be more precise and we have to look at the failure of the material, we need to use the flexure formula, the shear formula, and then we obtain that the maximum shear stress is equal to 3/2 V/A. And with this, we conclude the analysis of common cross sections that we can find when we have a certain axial load, torsional load, bending moment, or shear force.